Did you have a chance to try that homework problem?
I did.
Okay. So let's see that we can go to your screen and take a look at that. Let's see. Okay. All right. Oh, you put it right in the drawing program. Excellent. That was a good idea. All right. So one moment, and I'll take a look at this.
Okay.
Okay. So one thing we've talked about how is, especially if this is a test problem, you just want to be extra careful to take your time and double check your work here, because we saw when we were doing these in the tutoring, it's easy just to make careless mistakes about what the dimensions are. So that's why this is some good practice. Now, part C came out to be 0. Why did
Right.
it come out to be 0?
It's because the area that's the area below the curve, the area below the function is the same as the area that's below. I'm not sure how to word this. The area that's
You can use your cursor to point it out,
okay.
or your pencil.
Okay, the area that's positive is the same size as the area that's negative, so they cancel each other out.
Perfect. Yeah, that's exactly what I was going for. So notice you actually don't actually need to do any calculations for that. If you notice that both triangles have a base of 2 and a height of 2, so they must be equal, and therefore they must cancel. I'm not saying you shouldn't do the calculations. It's just as well to do the calculations, but it's interesting to see that in this case we could have eyeballed it and seen that the answer was 0. Looks like that one came out correctly. Then, what's the relationship to part D to the first 3 parts?
D is just the sum of all 3 parts.
Good. Oh, it looks like you noticed that because you wrote it out that way. Okay, good. So this is kind of a penalty for people that are working mechanically. If someone was just working mechanically without thinking, they would waste a lot of time on part D, is the point, when they could have just used their previous answers. So that's certainly something to watch out for in the test. If possible, you might reuse your previous answers. On the other hand, you have to be extra careful to make sure that's really justified. If there had been any overlap between the regions in A, B, and C, then you couldn't just add them together, because that would be double counting. Okay, well, it looks like I saw, we were talking about how it's easy to make careless mistakes on those, but it looks like you were careful. I think those answers all look correct. Good, so let's look at part 9. Let me take a look at this. It's increasing on 4,9 because f is positive on 4,9, and f equals g prime. Good. It looks like you were bucking for some extra credit there, because you put in where you have the local min and the local max as well. Okay, so that's a good idea, as long as you're confident. You wouldn't want to put in an answer that was wrong. But let's see, local min at 4, because it was decreasing, that looks right, and local max at 9. So yeah, so you might get a little extra credit for that. That's very good. Okay, great, excellent. So that's something we put quite a bit of time in. It's pretty sure you'll see another question similar to this on your test. So it looks like we made some good progress on that. Very good. Okay, all right, very good, excellent. So that was a successful problem. Let's see. Okay, well, part A is pretty straightforward. The only tricky part is to remember that you need a negative sign because the x is in the bottom limit of integration, and it looks like you got that correct. And you gave a justification. That's good. You said your justification was the Fundamental Theorem of Calculus. Part 1. Good. Let's look at part B. Okay, part B we got confused at, so I guess we haven't really learned that topic yet. So let's try that again. Here we're supposed to use the Fundamental Theorem of Calculus, part 1. And we're supposed to say that this derivative is this. Do you see how the fundamental theorem of calculus applies here and lets us get that the answer is 4x squared?
Yep.
Okay, so do you see the difference between these two lines? These are two completely different problems. When you're taking the derivative of a power function, you use the power rule. But when you're taking the derivative of a definite integral, you use the fundamental theorem of calculus. And it doesn't matter what type of function is on the inside here. It doesn't matter what this is. It doesn't matter whether it's a power function or a root function or a polynomial or a rational function. It makes absolutely no difference what this function is, because we're not actually going to modify this function in any way. All we're going to do is just plug x into that function. So these are two different cases. Okay.
I thought that's what I did. I don't know.
Okay, well, all right, maybe I'm on the wrong track. Let's go back to your screen and let me take another look at it. Maybe I got confused. Sorry. All right, let's take another look. 2x 5 plus 2x t squared. 1 second.
I guess the only thing I see that would be incorrect is this. Well, it should be in parentheses.
Okay, so I'm sorry, I screwed up. You're right. You were telling me that you hadn't done it, and I kept insisting that you had, but you were right and I was wrong. My bad. Okay, I got confused when I looked at this. You did something that made me think you were going to use the power rule, and then I jumped to an assumption. So that's good that you asked me to take another look at it here. Okay, so all that little lesson there where I was trying to teach you not to use the power rule, I guess that was completely useless because you hadn't done that anyway. All right. We still probably would lose a little bit of credit here. We haven't quite written this out correctly, and I think based on the sample test, the instructors are pretty picky about how we write this. But you did end up with the right answer, so we just have to make a little modification here. But your basic idea here was correct. I was confused. All right, let's see. So first of all, the thing that confused me is that you used the distributive law, and you rewrote it as 5t plus t cubed. Now, that's not really necessary here. You don't have to use the distributive law because you're not actually taking the derivative of that function. So you could have just left it the way it was originally. So when I saw you were using the distributive law, I jumped to the wrong assumption and I thought you were using the power rule. So you don't have to use the distributive law here, but if it makes you feel more comfortable, it's actually fine. So that's not a mistake. If it makes you feel more comfortable to use the distributive law here, that's actually perfectly fine. I just wanted to point out it's not necessary. All right. I think it would be a good idea. I think they're pretty picky here about making sure that you're justifying your steps. So I think it would be good to have a middle line where you said that g of x equals derivative outside times derivative inside to show that you're clearly using the chain rule here. So that would go, yeah, right on that line.
Maybe it would be worth seeing how we would do this if we didn't distribute.
Sure. Although, like I said, there's absolutely no mistake in the way you did it. But yeah, it's perfectly fine. We can go through it that way too. Okay, good. And like I say, I think they're pretty picky about justifying your steps here. So next to that line you just wrote, we should write chain rule.
Okay.
I think that would be a good thing to do on the test, to justify your steps here. Okay, and the next line is the only line where you made a mistake. You would lose a little credit for that. So what's your inside function there?
The inside function is the definite integral of 5t plus t cubed. And I guess I should have more with respect to t.
Yeah, so that's one little mistake. That's something we have to put in there. That's actually, though, that's the outside function, not the inside function. The inside function is the 2x. Now, what you forgot is, remember that when we use the chain rule with this approach, we have to make up a new variable. You actually did that in the next step, but we needed to do it in that step. What's the variable that we're using to stand for the inside function?
U.
That's right. Now, the thing you're erasing right now was not the problem. The thing that was okay. We can leave that as 2x. But the point is now we have to put that u into the left-hand term for the outside function. Okay. That was the one I didn't see, so that's what messed me up. I didn't see that, so I assumed you weren't using the chain rule. When I saw you doing that, I thought you were doing some kind of product rule or something, I guess, because you didn't put the u in there, but I should have taken my time more and looked at what you were doing. All right, so anyway, we probably would lose a little credit for not putting that in correctly, but now that looks like that's right. So the prime should be outside of the parenthesis there. And then you can use, and then you used the derivative rules. And then you used, right. So then what was the step where you used the Fundamental Theorem of Calculus, part 1? What was the step where you used the Fundamental Theorem?
This step.
Good. So that's the one that should be labeled as Fundamental Theorem of Calculus, part 1, not the one after it. So I think those are important labels to put in on the test to show that we understand why we're doing what we're doing. So the key thing is you can't use the Fundamental Theorem of Calculus unless there's just a single variable in the limit of integration. That was the usefulness of the chain rule. The usefulness of the chain rule is we need to have just one single variable as our variable for integration. Okay, so first we have to put in the u there, and then we're taking the derivative with respect to u. Okay, but you did end up with the correct answer. So there was a couple notational mistakes in the middle there that might have lost us credit, but I was the one that was more confused about this one. You were generally on the right track with that. Okay, so I think those little details are important for getting full credit based on the sample test, but now I think we have it correct. Okay, so let's try this again without using the distributive rule.
Okay. I'm just gonna rewrite this. G of x. Okay.
So it looks like you're about to use the chain rule. Let's be a little bit more systematic. Remember, I think it'll be safer when you do this to write derivative outside times derivative inside as your first step.
Okay.
Because I think it's important to them that you're justifying your steps here. And let's justify that last step. That last step was the chain rule. So we should make a note so the grader knows that we know what we're doing.
Okay.
Okay, now let's go back. Let's take our time on this. We want to make sure we're getting this correct. So what does u stand for here?
The inside function.
So what specifically does it stand for?
2x.
Good. Notice it doesn't stand for t. So we shouldn't be changing the t's. We should only be changing the 2x into a u. The t's stay the same. We're plugging the u in for the 2x, but we're not changing the t's.
I'm still having an issue seeing how to apply chain rule here, but I'm just kind of, I guess need to memorize it. Okay.
What did you just apply to figure out that that was u times 5 plus u squared?
Fundamental Theorem of Calculus.
Yeah, that's where we're using the fundamental. So I can see why you plugged in u in the previous step. I can see how it's confusing, because we are plugging in u now. But the point is, we plug in u when we take the derivative. Once we get rid of the integral sign, that's when we plug in the u. And that's not really related to the chain rule. That's just the way the fundamental theorem works. Okay, so that looks like we have that written down correctly now.
So plug into x for u. It's just the same answer. 10x plus. Something's wrong.
Okay.
So this was cubed, not squared.
Careful, I think you made a change that's not correct. I think it was a t squared. Now, so are those two answers at the bottom the same or not? Well, if you look at that answer there at the bottom, notice that you could use the distributive rule on that answer at the bottom, correct?
Mm-hmm.
What's 2x times 5?
10x.
Good. And what's 2x times 2x times 2x? That's 2x cubed, right? If you use the distributive law at the bottom, you'd be doing 2x times 2x squared, right? Mm-hmm. But that just means 2x times 2x times 2x, right?
Right.
And that's 2x cubed.
Okay.
Do you see how that matches what you have on top then?
Mm-hmm.
Yeah. Okay. Yeah. Now, of course, on the test, there would be no need to do it two ways and see if you got the same answer. But if we do the algebra correctly, we can see they really did come out the same. So like I said, the method you used on top isn't wrong, but it's really unnecessary to use the distributive law there because we're not really taking the derivative of what's inside the definite integral. We're taking the derivative of the definite integral, and that doesn't require any manipulation of the function that's there. Okay, so your original answer was correct. I was the one that was confused, not you. But there were a couple notational things that probably might have lost you some credit on there that we saw when we went back. Let's go to my screen. Okay, so think about how would you take this derivative? Can we just apply the rule for the derivative of a sine directly to this?
I don't think, no, we can't.
No, because that only works when you're taking the sine of a single variable all by itself. So we need something that we need to simplify this so we can apply the rule for sines here. So you remember what's the name of the tool or the technique we're going to use to evaluate this?
Chain rule.
So let's just look one more time at how the chain rule works. Here's the basic trick for the chain rule. So the trick, remember, is remember that the problem here is this function is too complicated to take the derivative of it, right? This function is too complicated. We don't know how to take this derivative. How could I simplify this So we could take its derivative. Well, what we need is we need to have just one single variable here, right? We can't have a variable plus a number. If there was only one single variable here, we'd be home free. So that's the basic trick of the chain rule. You take your complicated function and you plug u in somewhere. How do you know where to plug in the u? Well, you plug it in wherever it will be helpful in order to simplify things into something you know how to take the derivative of. Why did we plug the u in here? Because that was what we needed to have something that we can take the derivative of. This is now called the outside function. And now, remember, u stands for the inside function. So what's the inside function here?
2x.
Because 2x equals u. Do you see why this is called the inside function? Because you could plug the 2x in to this position. You could plug the 2x inside of the u into this outside function. This is called the inside function because it's really hidden inside of this u. This is called the inside function because it's hidden inside of the u, and this is called the outside because that's the opposite of the inside. Okay, that's all there is to it. That's the basic trick of the chain rule. So suppose you had something like let's say you were asked to find this derivative. Well, can we apply the power rule to this directly? Can we apply the power rule directly? No. You can only apply the power rule when you have a single variable all by itself to an exponent. So what would be the name of the trick we can use to simplify this so we can apply the power rule?
Chain rule?
Yeah. So the first step for doing the chain rule is to write this. Now, maybe it helps to start. I'm just going to start by just recopying the original function. Here's the original function. Now remember, this function isn't going to work for us because we can't apply the power rule to this. So somehow I need to make a substitution. I need to make a substitution so I can apply the power rule. How do I know what to do? Well, that's hard. That takes practice and judgment. But I think we've practiced enough to see that the trick here is get rid of this whole mess inside the parenthesis and just replace it with u. Because can we apply the power rule to this?
Yep.
Yeah, and now we don't even need these parentheses. So that's the trick. The trick is to plug in, to get rid of the complicating stuff that's messing us up and replace it just with a single variable u, because then we can apply our simple derivative rules. Now the only way that's going to work is now if I also take the derivative of the inside function. Well, what is the inside function here?
X squared plus 3x.
Because that's what the u stands for. And do you see why this is called the inside function? Because you could plug it inside of the u. And the outside function is the u cubed, because it's what you could plug the inside function into. And hopefully, and now at this point, you would probably already know how to continue using the chain rule, because now we can apply. So can we apply the simple rule for taking the derivative of a sine to this expression? Yeah, and can we apply the simple rule for taking the derivative of a power function to this expression?
Yep.
So we're kind of home free with those two. Well, now, so here's another derivative. Now here we're trying to take the derivative of a definite integral. Here we're trying to take the derivative of a definite integral. Well, there's a trick or a theorem for taking the derivative of definite integrals. The theorem for taking the derivative of definite integrals is the Fundamental Theorem of Calculus, part 1. But does the Fundamental Theorem of Calculus apply directly to this particular definite integral?
Yes.
The answer is no, because the analogy here is you can only apply the simple rule for taking the derivative of a sine when the sine is being taken for a single variable all by itself. You can only apply the simple rule for taking the derivative of a power function when the base is a single variable all by itself. And you can only apply the simple rule for taking the derivative of a definite integral when the limit of integration is a single variable all by itself. In order to apply the fundamental theorem of calculus, this has to be a single variable all by itself. But it's not. It's a number times a variable. So the fundamental theorem of calculus part 1 doesn't apply to this yet. But there's a trick that we can use to make it apply. It's the same trick we used in the 2 previous cases. We can use the chain rule. Okay, so here's the thing we were trying to take the derivative of originally, and we decided this was too hard. This is too hard. We don't know how to take the derivative of this. The fundamental theorem of calculus part 1 doesn't apply here. Why doesn't it apply? Well, what I was going for is the fundamental theorem of calculus doesn't apply here because it only applies when this top limit of integration is a single variable all by itself. But here it's a number times a variable. So what we need to do is we need to simplify this term. We need to simplify this term so that it's just one single variable. This is the problem. I guess that's what I'm trying to say. The way that you figure out how to apply the chain rule is you figure out what the problem is. The problem here was the 2x. We had to replace that with a single variable so we could apply the rule for taking the derivative of a sine. The problem here was the x squared plus 3x. We had to replace that with a single variable so we could apply the power rule. And the problem here is the 2x. We need to replace that with a single variable so that we can apply the chain rule. We need to replace that with a single variable so that we can apply the fundamental theorem of calculus, part 1. So we're going to use the same trick that we used in the previous cases. We erase the part that's giving us a problem and replace that just with u. Okay, and this now becomes the outside function. And then what's the inside function?
(2x).
That's right, because u is always the inside function. U is always the inside function, and what does u stand for here?
2x.
Now, do you see why this is called the inside function? It's called the inside function because you could plug it inside of this function here. You could plug it into the u. So this is called the inside function because it's really hidden inside of that u. And this is called the outside function because it's the opposite of the inside function. Do you see why we would not put a u in for t here? Because what does u stand for? What does u stand for here?
It stands for 2x.
Right, it doesn't stand for t. So there wouldn't make any sense to start putting in u's here because does u equal t? No. U stands for 2x, so we're not going to be plugging in a u here. We just plugged the u in for the part that was giving us trouble. This wasn't giving us any trouble. We know we can handle this just fine. The part of this that was giving us trouble is that this limit of integration was too complicated. You were going to say? What were you saying?
I mean, I guess I should just memorize it, but I look at the problem and I want to make t squared plus 5tu. So I guess
you're saying you want to. Oh, you're saying you want to do maybe this. You're saying you want to just plug in u for this whole middle thing.
For something like that, yeah.
Okay. Now, why you could do that, but the problem is it wouldn't be helpful because this was not the problem. This was not the difficulty here. The difficulty was that this limit of integration was too complicated. The reason we couldn't apply the fundamental theorem of calculus is that this limit of integration was too complicated. This term here wasn't giving us any trouble. So one thing I should maybe explain is there's many different ways you can assign the inside function and the outside function. On any problem, there's many different ways you can assign the inside function and the outside function, but there's usually only one way that's helpful. There's usually only one way that will help you to solve the problem. So maybe in a sense you could plug the u in here on the middle, but that wouldn't do us any good because the fundamental theorem of calculus still doesn't apply here. It still doesn't apply because this wasn't the problem. The problem was that this limit of integration was too complicated. the theorem of calculus only applies when the limit of integration is a single variable all by itself without any numbers. So that's the basic reason. Yeah, maybe you're right. Maybe we could plug in u for this, but why should we? It wouldn't help us. We have to do something that's actually going to help us to solve the problem. So plugging something in for this middle term doesn't help us, and so even though it might be legal, it's not the thing that we're going to do in this case. Or maybe just plug. On the other hand, this was the part that was giving us difficulty, so that's where we want to plug in the u. And since we plugged in the u for 2x, now it certainly wouldn't make any sense to plug a u in here because u doesn't stand for t here. It stands for the 2x. Okay. All right, and then I'll just go ahead and finish off that part of the problem. So now the fundamental theorem of calculus does apply. The fundamental theorem, also I'll write down here we were using the chain rule. Whoops. So here we were using the chain rule. So now the fundamental theorem of calculus does apply, because now there's just a single variable all by itself in this limit of integration. And the fundamental theorem of calculus says that the way you take the derivative of a definite integral is that you just write down the function that you were taking the integral of, but you plug in the variable. You plug in the limit of integration. So we'll plug in u for t, and u squared here, and 5u. And then this derivative is just 2. So I can see how this is confusing, because I was just telling you a moment ago not to plug in u for t, and now in this step I am plugging in u for t. But these are two separate steps. This step here was a chain rule step. Well, we don't plug in u for t when we're using the chain rule. When we're using the chain rule, we're using the plugging in the u for the 2x. But now when we use the fundamental theorem of calculus, part 1, now the fundamental theorem of calculus says now we really do plug in the u for t. So I can see how it's confusing, because we did plug the u in for t eventually, but to show we understand, we have to plug it in when it's justified. It's not justified as part of the chain rule, but it is justified now when we take the derivative using the fundamental theorem. And now we have to get rid of the u. So remember that u equals 2x. So we'll plug in a 2x here. And this would be a 2x squared. And this would be a 2x, 2x squared, 5 plus 2x. Okay. And here we have the answer. Okay. So anyway, that's the best I can do. That's the best I can do to explain how the chain rule works here. Hopefully that helped a little bit. And if it didn't, like you said, you'll just have to memorize the steps. That's the best I can do to explain it. And if we're still having trouble with it, I guess we'll just have to kind of memorize the steps here, because you're pretty sure to see this type of example on the exam. What I was trying to show you is that if you accept how we used the chain rule here, and you accept how we used the chain rule here, we should accept how we used the chain rule here, because it was exactly identical. Here the problem was the 2x, so we replaced it with a u. Here the problem was the x squared plus 3x, so we replaced it with a u. Do you see why I'm calling it the problem? That's the problem because that's the thing that's preventing us from taking the derivative. And here the problem was the 2x. Do you see why I'm calling that the problem? It's a problem because it's preventing us from taking the derivative. So that's the thing we want to replace with the u. Once we've done that, then we can take the derivative. Okay, that's the best I can do to explain that. Okay, so let's see.
I felt like I knew how to do these, but
well, like I said, I was as confused on that last problem as you were. You did get the problem right. There were some notational mistakes that I think would have lost you some credit, but you did get the problem correct. Well, let's practice this one more time to make sure that we can get it right. Not just get the right answer, but also justify our steps so we can get full credit. So try this on your screen. Try to use the approach we were talking about.
So g of x equals t times 8 minus t squared with respect to t between 2 and 4x. Take the derivative inside, outside, derivative of that.
Okay, let me give you a little help with this. So first of all, let's write down that middle step where we say g prime of x equals derivative outside times derivative inside. Okay, now I noticed that in this problem, and that was the chain rule, so we can write down that we're using the chain rule there. I noticed in this problem you're using the symbol u. What does u stand for on this problem?
The inside function.
Good, so what specifically does it stand for?
4x.
Good. So notice it doesn't stand for 8 minus t squared. So you actually ended up plugging the u into two different places. You plugged it in for the 4x, which was good, because it really does stand for 4x. But you also plugged it in for the 8 minus t squared, and that was not so good because it doesn't stand for that. So that's in your third line. That third line has to be fixed. It was correct to plug the u in the limit of integration, but we shouldn't have plugged the u in for the 8 minus t squared. We could just leave that as 8 minus t squared. So we can go back and erase that u if you see the one I'm talking about, and just keep that as 8 minus t squared.
I thought we were trying to put u back into this.
And let's put in the dt as well. So that step there, let's label that as the chain rule as well. So remember, the thing that was giving us trouble was the 4x. That was giving us trouble because that was too complicated a limit to take the integral of it, so we had to plug the u in for 4x. But there was no reason to plug the u into the other places. Now we can apply the Fundamental Theorem of Calculus, part 1. So now we're actually going, let's put the prime up in that previous line as well. Now we can apply the Fundamental Theorem of Calculus to that, because now the upper limit of integration is just a single variable, all by itself. So how do you apply the Fundamental Theorem of Calculus? Well, this is where now you do plug the u into the function that you were taking the integral of. Now is when we plug the u in for the t. Now is when you plug u in for t, basically, into that function. We get rid of the integral sign, and now is when we plug the u in for t. I guess that's what's causing us the confusion, knowing when to plug the u in for t and when we don't. So now we also plug the u in for the other t as well. That's right, it's still u squared. Okay, good. So first of all, we plug u in for the limit of integration. And then in the next step, when we take the derivative, we plug the u in for t. That's what's giving us trouble. So now we have one more line to finish the problem. Okay, those are good parentheses. Good. Okay, that's correct. Just to make sure this is correct for your notes, go back up to the third line. There should be a right parenthesis after the 8 minus t squared. 8 minus t squared, then a right parenthesis, and then the dt. All right. And maybe the right parenthesis after the dt we don't need.
Wow.
That parenthesis got put in the wrong place. Okay, well, obviously we're getting somewhat confused about these, but I'm not going to spend any more time on this here. I think we might just be having a little bit of a mental block, or maybe it's not worth trying to understand it in any more detail. So the pattern here is not super complicated. So you have a bunch of correct solved examples of these now in your notes. So if you study those examples, you should be able to follow that pattern, even if we're not totally understanding each step. But the basic point here is we're having trouble knowing when to plug u in for each thing. So the pattern is, first, you plug u in for the limit of integration. That's the chain rule. Then you plug u in for t. That's the fundamental theorem of calculus. And we're getting confused because we're mixing up those steps. So just to repeat, first, we plug u in for the limit of integration. That's the chain rule. Then we plug u in for t in the next step. That's the fundamental theorem of calculus. The reason we're getting confused is we're confusing those two steps. So I think if you study, we have like 5 or 6 examples of these in our notes now. So if you study those examples, I think you'll be able to follow that pattern. Okay, well, I guess that's about the best that we can do with that topic. But like I said, I was the one, I kind of messed you up here because I was telling you got the first problem wrong when you really got it right. I think that might have shaken your confidence in your own steps. Your first approach here was not so far off. It was me who was confused at first, not me. I was confused, and then I infected you with my own confusion a little bit. Okay, I'm going to go back to my screen. Okay, I'm not going to do any more of those with you today during the tutoring, but let me write down 2 more homework problems that you can try to practice that. Okay, tell me when you have those copied.
Yeah.
Okay, so what I would recommend is first, like I say, I think we have about 6 complete solved examples of these types of problems, and they're all almost identical to each other. So my recommendation is just go back over your notes from today and the day before, and look at every single example that we've already done and see if you can see the pattern in there. And the key thing is you have to see when and where we plug u in for the various terms. First, we plug u in for the limit of integration. That's the chain rule. Then we plug u in for t. That's the fundamental theorem of calculus. So if you look for that pattern in the previous examples, hopefully that'll be apparent. And then hopefully when you feel comfortable with that, then you can try these 2 problems and try writing them out the same way we've been putting in our notes. So I've been trying to make sure that in your notes all of the examples were written out clearly and specifically, because I think they're going to be picky about that in the grading to make sure that you justified the steps. And then after you do these, you should be able to go back then and check against your previous examples and see if they really match the pattern. So I know we were having some trouble and having some confusion with these today, but sometimes that's just kind of a mental block. And if you come back to it a few hours later, things might be clearer. So you can come back to this somewhat later and take a look at it. This is the problem from, is this the problem that, the homework problem?
Yep.
Yeah, okay, so let me take a look. Okay, first problem was pretty straightforward. You just have to remember to put the negative sign in because the variable is in the bottom limit of integration, and you did that. And you also justified yourself by saying that that was the fundamental theorem of calculus, part 1. So let me take a look at part B. Okay, well, that's a type of problem that has given us quite a bit of trouble. I think you'd said yesterday you weren't quite understanding the logic behind the chain rule there. So I don't know, maybe you had a time to go back and think it through again, or maybe you just kind of memorized the pattern. But either way, that was the right answer, and also the correct notation for that. So I think that's some good progress on those problems. It looks like pretty likely that'll be on the test. These videos are offered on a pay what you like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.